and welcome to the first video of the FP2 chapter, Further Argand Diagrams. Prepare yourself for more complex numbers. On the screen is a starter not to do with complex numbers, but this will come in heavily to our chapter. If you've got time, draw the locus of points for each of these 4 things from your GCSE work. About a point, you should know that will generate a circle. Equidistant from 2 points will generate a line that is perpendicular to the line segment joining those 2 points. Equidistant from 2 lines will produce a line that bisects that angle, and about a line will produce something that kind of looks like a running track. Parallel on either side, and then a semicircle on each end. In this chapter, we're going to represent basic loci on an Argand diagram. Then in the next video we will represent more loci on an Argand diagram. Between these 2 videos there will be 5 standard results for you to know, and I've split them into ones to do with the modulus and ones to do with the argument, which is a bit different to the textbook. And then in the 3rd video I'll go through all the textbook examples for all 5 of those. Then we'll move on to representing regions on an Argand diagram, and finally transforming loci from one complex plane to another. But before we get started with these basic loci, we just need to quickly look at D, the distance between Z1 and Z2, 2 points on the complex plane in this Argand diagram. So what is D? On the one hand, you know using Pythagoras, D is very easy to find. Find the difference in the real parts and the difference in the imaginary parts, and square them, and then do the square root of their addition. No problem. But we just need to connect that with the modulus to help us in this chapter. So looking at what the modulus is, if we do the modulus of Z2 minus Z1, and then substitute in x plus yi for each of those, then we collect the real parts and the imaginary parts together, like this. Then removing the modulus by remembering that the modulus means the square root of the real squared plus the imaginary squared, which is effectively what we did here for D, Pythagoras again, then we can get this statement, because the real part of this full complex number in here is x2 minus x1, square that, and the imaginary part, y2 minus y1, square that, add them together, square root it, and this, you'll notice, is the same as this. So this lets us connect D, the distance between 2 points, with their modulus statement Z2 minus Z1, or Z1 minus Z2, because of course that would produce the same end result. This is a very useful statement. This is a very useful thing to remember about the modulus. We will use both of these in this video, so here we go. First standard result is this. What locus does this statement represent on an Argand diagram? Let's have a think. From what we just said on the previous screen, Z minus Z1 is saying the distance between the 2 points Z and Z1. Here Z1 is going to be a fixed point that we would know, and Z will be a variable point. The distance between them we're going to fix as the constant A. So if Z is variable, Z can be anywhere on the Argand diagram so long as it fits this rule that the distance from Z1 is a constant A. And I hope from our starter you will already have in your mind that what this will give you is a circle of radius A and center Z1. So Z is variable, but it's kept at a fixed distance from this point here. That's what this statement means. So our first standard result is this. You must remember this, that a locus of this type describes a circle with center, whatever this complex number is, and radius, whatever this constant is. Quick example of that. Let's say Z minus 2 minus 2i equals 10. First of all, be careful with your negatives. It must be in this format. So to really make that clear, I would change that into Z minus brackets 2 plus 2i equals 10. So what this is saying is the distance from Z, your variable point in green, from the point 2 plus 2i, which is at 2, 2 on your Argand diagram, the distance from here to here is fixed at 10 units. So the center of the circle is not -2, but 2, 2. And the radius of the circle, of course, is 10. Now to find the Cartesian equation of this circle, you've got two options. You can either use the fact that you know the center and the radius from the Argand diagram here, and just write the equation as you know it from your previous work, or you can use this equation as a starting point here, substitute x plus yi for your z, and then remove the modulus by grouping the real parts. So we've got x minus 2 plus y minus 2 here. And then we can take the real part, square that, the imaginary part, square that, add them together and square root the result in order to remove the modulus sign. That gives us this result. And then square both sides to give the circle equation you would have had from using the information in the question. 2, 2 is the center point, so we've got -2 here and a -2 here. 10 is the radius, so we've got 10 squared, 100 here. Now it might seem like that's a strange way of doing it if you know how to go from this information to this line directly, but this is a very simple example of the general process that we're going to use for more complicated loci. Okay, that's standard result 1. Standard result 2 is, what does this mean? So if we decompose what this means bit by bit from what we've said so far, this side is the distance of z from z1, where z again is a variable point and z1 is a fixed point. And this is the distance of z from z2, where z2 is another fixed point, but this z is still the same variable point z. So we've got a setup like this, where this distance and this distance are equal. And if z can vary while keeping these two distances equal to one another, then we get another familiar locus, which is the perpendicular bisector of the line segment z1, z2. And this is our standard result number 2, which you also have to remember. Another example. Let's put in 2, 2, the same point we had before, -2, -2i, -7, -6i, remembering again the minuses here. That gives you the complex point 7, 6. And what you might be asked here is to find the Cartesian equation of this straight line here. And again, there are two ways you can do this. As with the previous example, you could work from the information you've got here in a way that you've done before. Find the midpoint of this line, that's on this line here as well. Find the gradient of this line, and then use m1, m2 equals -1 to find the gradient of this line, and then put that together to find the equation of this line. Or, again, you could use this as your starting point and follow that same method we had before. So we had x plus yi instead of z, but this time it comes up on both sides. Then group your real and imaginary parts in order to remove the modulus symbols in the next step. And again, to do that, we square both the real and the imaginary parts, add them together and square root them. So we've got the square root of x minus 2 squared plus y minus 2 squared here is equal to the square root of x minus 7 squared plus y minus 6 squared here. Now, as I square both sides to get rid of the square roots, I'm also going to open up all those brackets. So we get x squared minus 4x plus 4 plus y squared minus 4y plus 4 equals x squared minus 14x plus 49 plus y squared minus 12y plus 36. You can see we're going to get a straight line out of this because the x squareds cancel and the y squareds cancel. Now all we need to do is put this line equation into a familiar format, which will give us, in this case, 10x plus 8y plus 77 equals 0. So in the first example, we had a situation where doing this process was almost certainly slower than just using the information that you had in the diagram. Whereas here I would say it was about the same length of time. You had a few different steps to do to get the equation from the diagram here. With the third standard result, this process is definitely the easiest because it's not so easy to get the result from the diagram. So let's have a look at this third standard result. It looks quite similar to the second, but with this k in here, this is now not equidistant, but a fixed ratio between the two distances. We're going to have k greater than 0, k is a real number, and of course k is not equal to 1, just because if it was, it would be the second standard result. The result in this case I don't think is intuitive. But if you've got a fixed ratio between this distance and this distance, in my diagram that I've drawn here, k would be about 2. This is about 2 times bigger than this. And if z can vary with that ratio fixed, like this, it would give you a circle. Unfortunately, it's not easy to find the center or the radius of this circle. It's not as easy as it was before. It's not just z2 or z1. It's not just this distance or this distance. It's an unknown center and an unknown radius. And we have to use the method I've been using from the equation to find out what those are. But this is our third standard result. This statement describes a circle whose center and radius is to be found using algebra. So here is another example, and we will do this. So we've got z minus I, so your real part here is a 0, and the imaginary part is a 1. So just because it doesn't say it there, don't forget about those zeros. And that is going to equal 2 times this distance z from 6, 4 here. So this is roughly 2 times this. My diagram isn't perfect, but it gives you an idea. And what we need to do is what we did before. Replace z with x plus yi on both sides. And then we will collect the real and imaginary parts and get rid of the modulus symbols. To save a bit of space, I'm going to try and do these together. So here we've got x minus 0 effectively is the real part. So it's x squared plus y minus 1 squared square rooted. Over here we've got 2 times the square root of x minus 6 squared plus y minus 4 squared. Now you must be careful to keep this 2 here outside the square root, and then when you square everything, to remember to square this 2. That gives us 4 times everything inside the square root, which I will expand at the same time. And yes, these are often quite long questions like this. On the left, now apply that to 4x squared minus 48x plus 144 plus 4y squared, 32y, 64. Same thing on the left still. Collect everything together and make it into a circle equation. If the numbers were a little bit more awkward, you would have to be very careful here, but in this case I can just divide everything by 3 to simplify it all very nicely. That will not always be the case. And then do your usual completing the square process. And rearrange it to the usual format. Which gives us a circle with center 8, 5 and a radius of square root 20 or 2 root 5. And whether this k is a 2 or a 3 or a 4 doesn't make any difference to the process. It will just make the numbers more or less awkward. You will still end up with a circle at the end. Here is our third standard result then, and the general method for interpreting our basic loci was this. either go ahead and interpret it directly, like the circle that we had at the beginning, if you can. Otherwise, let z equal x plus yi, substitute that in, group the real and imaginary parts together, then get rid of the modulus using this definition here, and then just manipulate it to interpret the locus as you need to, into a straight line equation or into a circle equation in their usual formats. This gives a Cartesian equation for the locus every time, and it will also make it easier to understand and interpret the locus, even if the question doesn't need the Cartesian equation, it just needs you to say what it is. You might need to get the Cartesian equation in order to know what it is. A few examples to finish, one of each. For each of these loci, sketch the locus on an Argand diagram and find its Cartesian equation. So for part A, we've got one fairly straightforward. This is in the form z minus 5 plus 3i is equal to 3. So our complex number point is 5 on the real axis, 3 on the imaginary axis, here it is. And the radius of the circle is a 3, so it's going to come down and touch the real axis like this. Oh dear, my circle is not very circle-like, but that's good enough for a sketch. For the Cartesian equation, I won't go through the whole process, I'll just use what I know about circles, and this gives us x minus 5 squared plus y minus 3 squared equals the radius squared. For part B, we've got z minus 2 minus 3i is equal to z minus 1 plus 4i. So I've got the complex numbers minus 2 minus 3, that's down here somewhere, and minus 1, 4 is up here somewhere. So these are my 2 points, and I know that this is a perpendicular line through this, bisecting it, so it's roughly something like this. But to get the equation of this line, I am not going to use the diagram, I'm going to use the original equation here and use the method that we've been using throughout the video. So we've got x plus yi in place of z on the left, plus 2 plus 3i is equal to x plus yi in place of z on the right, plus 1 minus 4i. Group the real and imaginary parts and get rid of the modulus, so we've got x plus 2 squared plus y plus 3 squared, square rooted, but I'm going to square both sides anyway. X plus 1 squared plus y minus 4 squared, square rooted, but after I've squared both sides, both the square roots disappear. Be careful not to jump that on part C because of that 2, but in this case we get this. Now expand and simplify. Again, we can get rid of these because we should be ending up with a straight line. 14y plus 2x minus 4 is equal to 0. And I suppose now to complete my Argand diagram, because I know what this intercept is, I could put that on there. That will be 4 over 14 or 2 over 7. Third and final example for this video. We've got z1 is 6, z2 is minus 6 plus 9i. So 6 on the real axis, and then minus 6 plus 9i is over here somewhere for z2, and I don't know yet where the circle will be. So even to draw this, I'm going to need to go through the algebraic process of finding the Cartesian equation. So what we've got is x plus yi minus 6 on the left is equal to 2x plus yi plus 6 minus 9i on the right. Group the real and imaginary parts. So we've got x minus 6 squared plus y squared square rooted to get rid of the modulus is equal to 2 times the square root of x plus 6 squared plus y minus 9 squared, and then square everything, remembering that 2 in the middle needs to now become a 4. Expand the brackets at the same time. Gives us this on the left. and on the right, big brackets for that 4, x squared plus 12x plus 36 plus y squared minus 18y plus 81. Apply the 4. Nothing's changed on the left. Now we need to collect them and put them into a circle equation format. And again, we're fortunate that all of these numbers will divide by 3, which makes it much easier. And then complete the square. Our 144's cancel, which means our final answer is x plus 10 squared plus y minus 12 squared is equal to 100. So our circle has a centre minus 10, 12, which is not going to be accurate on my diagram, but let's say it's over here, and a radius of 10 units. So it won't touch the axis here, but it will touch the axis here, and it'll go around like this. What you should find, and as a good check that you've done it correctly, is that one of your original 2 points, Z1 or Z2, should be inside that circle, and one of them should be outside that circle, because there should always be a bit in the middle where the ratio of the distances puts the circle between them, and there'll always be a bit where it puts it on the opposite side of the center point. So that's a good quick check at the end. That's it for this first video. We've got 3 standard results so far, all to do with the modulus, but because I've left the argument loci to the next video, that means you can use some of the questions from exercise 4a and some from 4b. You'll have to decide which ones you can and cannot yet do. Or you could just watch the next video straight away and then do all of them. Maybe I'll see you there.